We're going to talk about two different concepts of waves, phase and superposition, and then we're going to combine those two concepts into this idea of constructive and destructive interference, how waves interact and cause interference. So let's start out with phase. Phase is a particular point in a cycle on a wave. So here's a standard sine graph. The phase at the point on a standard sine graph that has maximal amplitude is pi over 2. The spot where it comes back to the rest point would be pi. Minimum, or maximum negative, I should say, amplitude would be 3 pi over 2 would be the phase. And 2 pi is where the wave has come all the way back around. The phase is all the way back around 2 pi. So that's the spot on a sine graph, or the spot on a wave, the phase of it. Now, phase shift deals with whenever you actually change the location, the starting location of the wave. So here's a standard sine graph, once again in red, sine omega t here. But if I slit it back here, I have changed its starting position, I have changed its phase, and I'm actually going to draw that in for you in a different color. So now by sliding the sine graph to the left, starting at negative pi over 2, I actually have shifted the phase, and the equation for that, sine omega t plus pi over 2. Now that might seem somewhat confusing. I'm not going to go into the details mathematically of it, but since it's inside the sine function, this entire part would actually be referred to as the phase. This is a phase shift. It's slid to the left. Positive means you're sliding to the left, so you're sliding to negative pi over 2. Remember the entire wave equation, x equals x naught sine or cosine omega t plus phi, where phi here, this Greek letter phi, is actually what's referring to our phase shift. Let me see if I can't draw it a little bit better. Greek letter phi kind of looks like a 0 with a line through it. Sometimes you'll see it drawn like that also, maybe with a little bit more of an angle in there. Greek letter phi. So that's the idea there. Now let's slide it instead the other way. Let's slide it and start it at positive pi over 2. And so I drew that in green, and whenever you slide it to a positive pi over 2, so you're starting it here, you actually are going to omega t minus phi over 2. So that's phase shift. If you slide to the right, you use minus. If you slide to the left, you use plus. And of course, you could always continue. To draw the other side. That doesn't matter. You just look at where's the starting point in the wave. So here was the starting point. You know, if I continued my blue one on back, but here's the starting point of the wave, where it started up, the normal sine graph, where it started. In red, it's fairly obvious, right? It's here, there, for the starting position of the red graph, perfectly at the origin there. I also would point out this other thing. The difference between sine and cosine, sine and cosine are the identical equation. Just cosine, here's a standard cosine graph. Cosine is a sine graph that has been given a phase shift of pi over 2. I mean, check out the blue line here. This right here, which is sine omega t plus pi over 2, starting here, ends up being, compare these two, ends up being a perfect cosine graph. Now I want to give an even more important concept with this idea of phase shift, specifically being in phase and being out of phase. Let's start out with being in phase. Being in phase simply means that everything is lined up perfectly, that our wave, let's say I gave it a phase shift of pi over 2, so sine omega pi plus let's use 2 pi, not pi over 2, 2 pi, an entire length of the wave, starting somewhere way back that way, right? And by the time it hit negative pi, we'd be coming down like this, right? And then we'd be coming back up, here's the minimum. We'd be coming back up like that, and then we would continue on just as normal. So if I gave it a phase shift of 2 pi, right, then everything is in phase, meaning that everything lines up. Now let's talk about perfectly out of phase. Perfectly out of phase occurs whenever things are, if you will, opposite. So let's give it the sine graph a shift of just pi. So here's its starting position. Sine always starts coming up, right, and then comes down, and then continues to oscillate here. This would be considered out of phase with my original sine function omega t. Notice how where the original sine function is up, my phase shift with pi is down. Thus, this would be considered out of phase. So being in phase is going to be everything being lined up, and being out of phase would be whenever everything is opposite. Even more specifically, if you are in phase, if you're in phase, that means everything has the exact same phase or has a phase shift of 2 pi, aka 360 degrees. Okay? If you are out of phase, that means the phase difference between them, one of the waves has a phase shift of pi or 180 degrees. So if things are out of phase, they have one of the waves has a phase shift compared to the other of pi or 180 degrees difference. Superposition of waves refers to when two or more waves occupy the exact same space at the same time. They have the same, if you will, space and time. Whenever that occurs, their displacement of the particles, if you will, their amplitudes, you could interpret that loosely. The displacement of the particles would actually add. So here's an example. I have two wave pulses, one with an amplitude of 2, and the other with an amplitude of, it's going down, so -1. And they are moving opposite of each other. So the red wave is moving to your right, and the blue wave is moving to your left that way. Whenever they intersect, they will add. So I drew what they were originally in dashed lines, and the green and what you would actually see, and the total amplitude here would be a +1, because +2 from the red, right, plus -1 of the blue gives me a resulting wave, superpositioned wave, of +1. If you will, you could think of this in more loose terms. I have a really big up, I have a small down. Whenever they combine, I get a smaller up. Here's something, though, that might not feel intuitive. It might feel like that once these two intersect, then they should be forever intertwined. That's not the case. They actually are just occupying the same space and time, so you see a resultant, but they do continue on their way, and so they will continue to separate. The red will continue to move to the right, and the blue will continue to move to the left. So these are wave pulses opposite. Over here, this is compliments of Penn State again. Little demo that a professor did for us, not specifically for us, but for anyone who would like to use it. Here we have two wave pulses, one moving to the right, the other moving to the left. And notice whenever they intersect, they add up, and then once they continue to pass through each other, they continue along their ways just like they were before. Now, here's where we're going. This idea of phase shift or a phase difference between two waves and superposition can be combined into an idea that's very important, interference between two waves. If you have two waves that are perfectly in phase, like here I have a nice standard sine graph, right? Up, down, starts at the origin, and I have another nice perfect sine graph, meaning there is no phase difference between them. This blue one hasn't been slid back this way at all, or if it was, it might have been slid back 2 pi, which means it has the exact same phase. There is no phase difference between them. Because of that, if I were to overlap them, and that might not show up perfectly here, but we'll see if I can. If I were to overlap them, notice that they perfectly line up, at least as closely as I can get it to, right? So since they perfectly line up there, no phase difference, meaning that constructive interference would occur. Just like in the previous slide that we showed, at that point in time, you're actually up plus up is going to give you a big up. Down plus down will give you a big down there, shown over here in green. So this is called constructive interference, when two waves line up perfectly and there is no phase difference. Destructive interference, though, is the opposite. That occurs when two waves occupying the same space, superposition is going to happen, they're going to add up, so they occupy the same space and time, are completely out of phase. They are complete opposites. So here I have two sine graphs, right? One is a standard sine graph, right? The other has a phase shift of -pi. Another way you could write that is a negative sine graph, but I'm not going to worry about that math right now. So this has a phase shift, of pi. So we slide it left to -pi here. Whenever you do that, everything is completely opposite of each other. So let's come and drag it over there back to its -pi location. And you can see whenever one is up, the other is down. That is being completely out of phase. Whenever you're out of phase, there's a phase difference, or one has been shifted by pi. So if they have the same amplitude, up plus down, right, will equal nothing. And so all the ups and the downs would cancel each other out, assuming these two waves have the exact same amplitude. So that's destructive interference, whenever two waves are completely out of phase from each other. Let me give you a few more pictorial representations of that. So here I have two wave pulses moving opposite of each other. They both have a positive amplitude x. Whenever they intersect, and here, because of the wave speed, they seem to be perfectly intersected at 1 second here, you get a wave that is 2x, but they're going to continue on their way, right? So the red continues to the left and the blue continues to the right, both with the same amplitudes they had before, x. They just slide past each other, but where we care about this would be constructive interference, right? What we care about is whenever they are occupying the same spot in space at the exact same moment. So here's two waves. They have the exact same amplitude, same wavelength. This works much, much better if you have the same wavelength. Now, I should point out, if you don't have the same wavelength, these waves can still interfere, albeit not very often. Also, if the phase shift, because we're going to talk about this in destructive interference, you can have constructive and destructive interference occurring whenever you don't have perfectly in phase or perfectly out of phase. Eventually, things will overlap and add up. It just won't be as often, but I'm not going to worry about that and the idea of beats and everything else there. But here, you know, they're perfectly in phase with one another, so they add up. Wavelength remains constant. It's just the amplitude that grows. Destructive interference occurs whenever waves are perfectly out of phase, pi out of phase, or 180 degrees out of phase. So here I have one up, one down. They have the same amplitude, so they completely cancel each other out, and then they continue to move on their way whenever they don't occupy the same space and time. Same idea here. I also would like to point out that just because destructive interference occurs doesn't mean that they have to cancel each other out completely. One, if it has a much larger amplitude than the other, whenever they add, your resulting wave will just be smaller. It's almost like the two waves subtracted from each other. All right, so also notice this little demo we have going on up here. I have two sine waves, one sliding to the left and the other sliding to the right over here. And check out what's happening here if we were going to line these up. This wave is constantly changing. The resulting wave is constantly changing. It awfully looks like a standing wave. That's coming in the next video here. But whenever the crests line up here, like that right there, you get a maximum amplitude. And whenever the troughs line up like that, you get a maximum negative amplitude. And whenever a crest and a trough line up right there, then you're back at the rest point. They completely cancel each other out because they have the same amplitude, same frequency. Now, this idea of interference is very, very important, and we use it in so many different applications. For example, in acoustics, whenever you set up speakers, you want to make sure that across the room, because these speakers are pumping out, let's say you set up two speakers. These speakers are pumping out two waves, right, that are identical, but depending upon something called path difference, which we're going to get to, you could have constructive and destructive interference occurring around the room. And destructive interference at a concert isn't exactly something that you want, because whoever's in that seat that's experiencing the destructive interference can't really hear much. The volume is much, much lower. Doesn't make the concert as good for that person. So you have acoustical engineers that deal with that. We actually use constructive interference to create lasers, so constructive interference with light. And we'll get into many more of those details as we go. Main thing that I need you to cling to coming out of this video is if you have two waves perfectly in phase, no phase difference or a phase difference of 2 pi, meaning that an entire wave is able to come by before it has to start the next one and combine with the other wave. If there's no phase difference between the two waves, you will get constructive interference whenever they add. If you have a phase difference of pi or 180 degrees, they are out of phase and you will get destructive interference. No phase difference, constructive, perfectly out of phase, phase difference of pi, destructive interference.